Good afternoon. Welcome to the Commercial Building Energy Code presentation, part of the Michigan Uniform Energy Code. Funding for this presentation is provided by the Department of Energy. Down through the state of Michigan, it comes to Michigan State University School of Planning, Design, and Construction. This production has been produced by this group. We're trying to train everybody involved in the building process, from the design of buildings to the construction and operation of buildings, in the importance of energy conservation. We're trying to increase understanding and compliance with the code and make everybody a lot more conversant with energy conservation. This is an overview of our presentation. We're going to be talking about the need for energy codes, the status, the relationship of the energy code to the rest of the codes, and some means of complying with the codes. And the reason that we're concerned about energy is because it has such a major impact in our lives. Recently, you've seen rapid increases in the cost of energy. We now have concerns about the global environmental change, climate change, of which energy and the heat and waste gases from fuels make a big difference. And so we must now focus more and more on energy, where years ago it was very little of our concern. Buildings, as you see, according to the DOE, use almost 40% of all the energy consumed in the United States. And we, as a group of construction individuals involved in design, planning, construction, and maintenance of buildings, have an opportunity to make a big difference. The building energy codes cover the envelope of the building, which means the walls, the windows, the roof, the mechanical and electrical systems inside, and the plumbing systems. And a wonderful resource, in fact, from which much of this program was extracted, is a website called energycodes.gov. Put that in your favorites on your browser because you will be going here many times for reference material. It is a source of the ResCheck and ComCheck computer compliance programs. You can download publications and purchase publications from this website. And there is a section called Building Energy Codes University, which has resources for self-teaching, for reference, illustrations, all sorts of information regarding energy codes. This will be one of your major sources of information on this website. The status of the Michigan Energy Codes is the same as the status of all the rest of the building codes. It's part of the family of building codes. And as of March the 9th, of 2011, we have the new code cycle starting. The energy code is part of the family of building codes. And it is right along with the structural code that you're familiar with, which covers the construction of the building relating to its strength, resisting wind loads, resisting snow loads, the strength of the floors to resist internal weights and loads. The building code covers such things as fire-resistive construction and life safety issues such as means of egress in an emergency. Another one of the codes is the mechanical code, which covers heating and air conditioning equipment, ventilation. It provides the ventilation standards for healthful occupancy inside a building. It talks also about kitchen cooking equipment. Along with that comes the Michigan Plumbing Code. And the Plumbing Code primarily deals with health. Also is the Electrical Code. The states have adopted the National Electrical Code. And as part of the family of codes are the Residential and Commercial Energy Codes. The Residential Energy Code is the MUEC, Michigan Uniform Energy Code. And one chapter in this, Chapter 5, is the Commercial Energy Code, which refers to the ASHRAE Standard 90.1, 2007. So this is part of the family of codes. It has been for many years, although many people are not aware of the Energy Code and have ignored it in the past. It is now becoming more evident that we must comply with the provisions in the Energy Code. The ASHRAE standard comes with an addendum. It's in a process of continual updating, continuous maintenance, as the ASHRAE says. ASHRAE stands for the American Society of Heating, Refrigerating, Air Conditioning Engineers, an engineering society group, a national group, actually worldwide. that sponsors basic research. The addenda for the 2007 are not included. They have not been adopted by the state of Michigan. The user's manual for the ASHRAE 90.1 standard is a wonderful reference, and I encourage you to purchase this manual. However, it has not been adopted by the state of Michigan. It is not part of the Energy Code. It's a reference manual to aid you in understanding the code itself. The status of the energy codes all across the nation is monitored by a group called the Building Codes Assistance Project. And they have a website which shows a map of the United States and the state and the status of the code in the state. Darker is better. The darker blue means the more recent codes have been adopted. And as you can see, Michigan is among the darkest blue states, and it says that we meet or exceed the ASHRAE standard 90.1 2007 or equivalent. They also have a similar overview of the states regard to the residential energy code status. And as you can see also with the residential code, Michigan as of the 9th of March meets or exceeds the 2009 International Energy Conservation Code or the equivalent. And here it is from the Michigan website. This is actually the online Code Environment and Advocacy Network, which is called OCEAN. And they monitor also the status of the codes, and there they're saying that on the 9th of March, Michigan started its new cycle. Michigan adopted the International Energy Conservation Code, but made amendments to it. The International Code is used by all different states, but the amendments changed it to the point where they published a customized version. And here it is. It's available for purchase at the state of Michigan. The cost is $38. Chapter 4 in here is the residential code. Chapter 5 of the IECC has been deleted in its entirety and replaced with one page which adopts and refers to the ASHRAE code as the commercial code with amendments. Very few amendments. When you purchase the commercial code book, you will get several pages which are Part 10A, the Michigan Uniform Energy Code. Part 10A is the commercial amendments to the ASHRAE code, the ASHRAE standard 90.1. But Part 10A is the commercial portion, and it's dependent on the language in Part 10, which is the residential, so they fit together. And we're going to cover primarily the prescriptive approach to complying with the Energy Code in our presentation today. It is possible to purchase a PDF copy of the standard from the ASHRAE website at a reduced price of $19, made possible by funding from the Department of Energy. If you wish a printed version of it, it is $119. And so the code is available in a number of formats. It can be expensive, but the code is necessary. It's part of the family of codes that we must purchase every 3 years as they're renewed. There are several tools in complying with the codes. If we use the prescriptive approach, as we're going to be doing today, which means do it like it's printed and you're home free, then you don't have to worry about any software compliance, no computer programs at all. However, if it's impossible for you to meet the prescriptive approach for one reason or another, the way the building is designed, then there are other methods, and these are using computers. And this program called ComCheck is written by the Department of Energy, Pacific Northwest National Laboratories, and it utilizes a U times A. U means the heat transfer through a wall or a surface, times the area, and it's a trade-off program which allows a portion of a building to exceed the code to balance out another portion of the envelope which is deficient. Then there's also a whole family of programs that are privately produced that can also be used. And these are energy analysis programs that are on the market from Carrier, from Trane, from the Department of Energy, eQuest, DOE2. The standard that we have, the ASHRAE 90.1 2007, replaces the 90.1 1999, which was our commercial energy code up through March the 8th of this year. This is an outline of the chapters in the code. We're going to be primarily dealing with chapter 5, 6, 7, 8, and 9. We have definitions in chapter 3, where it applies in chapter 4, and we have some references down here in section 12, and section 11 is an outline of a computer program the energy cost budget method, which we will be discussing shortly. In the appendices, the state of Michigan has adopted A through D. They have not adopted E, F, and G. Now, Appendix G is used for the LEED performance rating method. It is a voluntary system that is not mandatory. It's not required by law. But if you choose to design your building and apply for LEED credits, then you will be using Appendix G. Appendix A is a very large appendix with a whole bunch of wall and ceiling and roof combinations of elements that have been pre-calculated and U values calculated for them. Appendix B is the climate criteria. This is the criteria for analyzing the climatic data. The building envelope trade-off option is outlined in Appendix C, and that also requires a computer analysis. Appendix D is the climatic data. Section 1, the purpose of the whole scope is to provide minimum energy requirements. Now, the commercial code applies to commercial buildings. So it says, except low-rise residential buildings. That means residential buildings 1, 2, and 3 stories must meet the residential energy code, a separate portion of the MUEC. So motels and hotels 1, 2, and 3 story fall under the commercial energy code. Residential properties 4 stories and more fall under the commercial energy code. High-rise apartment buildings are commercial. The scope covers new buildings, new portions of buildings, and new systems in existing buildings. In other words, you're replacing heating and air conditioning equipment. The equipment must now comply with the new energy code, wherever you're not touching the rest of the building. And with a building, if it's not heated, the code doesn't apply. If it's heated minimally, the code doesn't apply. Less than 1 watt per square foot, which equates to 3.4 BTUs per hour per square foot. So if you heat the building less than that, the code does not apply. Or if you cool and air condition a building less than 5 BTUs per hour per square foot, the code does not apply. So minimally heated or minimally cooled buildings does not apply. But even though the building envelope may not be required to comply with the new energy code, the systems in the building must, the heating and air conditioning and plumbing systems. There are a number of exceptions that apply. Obviously, we talked about very little heating or cooling below those limits. Residential structures, buildings that don't use any power at all, any electricity or fossil fuel, or process and industrial buildings. The building itself, the building envelope, has to comply with the requirements of the energy code, but the processes of manufacturing within the building do not. There are 10 pages of definitions. Some have been changed from the 99 code. And in the body of the text, if you see a word that's italicized, that word appears in the definition section. Obviously, it applies to new buildings, additions to existing buildings, alterations, and replacements of portions of existing buildings, and changes in space conditioning. If you have a space that is not conditioned, it is not occupied, it's storage, and you change the usage of that space to one for human occupancy, then you must bring the provisions into compliance with the code. We have to submit some documentation that's outlined in section 4.2 as part of the building code construction permit application. We have to have materials and equipment labeled. We'll talk about the labeling later on. And the code does not intend to limit your ingenuity in constructing or designing a new building. It does not intend to limit the architect's creativity. If there are things, systems that do not appear in the code, are not labeled in a certain way, cannot be, or are too new to have been tested, talk to your building official. The building official can make a judgment and say, yes, let's give it a try. You can demonstrate compliance in some manner. Section 4 is the administration and enforcement section, which states, among other things, that new buildings, additions, alterations, replacements, and changes in space conditioning fall under the requirements of various following sections of the standard. And there are some exceptions for the code where it applies. One is historic buildings that are on the National Register of Historic Places, or the local city, township, the local governmental agency has designated as a historic district, such as the Indian Village District down on Jefferson Avenue in Detroit. Also, if the building is eligible for listing by the U.S. Secretary of the Interior, eligible, not listed, but just eligible, it also need not comply with the Energy Code. And here's an interesting statement. If the building's annual energy consumption is the same as a building that meets the requirements of sections 5 through 10. Now that's kind of an interesting way of phrasing it, but it says that you might have a building that's the same as another that does meet the requirement. And you can make alterations in there without having to go through the compliance procedures, as long as you're not increasing its energy consumption. There are a number of methods for demonstrating compliance with the new Energy Code. There's a prescriptive option that we're going to be talking about today. There's a trade-off option, which is calculated in the ComCheck program, or the energy cost budget method, which is a computer simulation, and a simplified method that applies in a very narrow range. We're going to talk about the building envelope first. There are certain things that we have to do no matter which compliance method we choose, and they're called mandatory provisions. Section 5 is the beginning of the building envelope, or you might say the architectural portion. It talks about the compliance method. The simplified building method is not allowed for the architectural portion of the compliance, the building envelope portion. It does have some mandatory provisions that apply to insulation, windows and doors. Windows and doors are called fenestration, and air leakage of the structure. The prescriptive building envelope option is what we're going to be talking about today. It talks about opaque areas of the building, which are walls and ceilings and roofs, and fenestration, which are doors and windows and skylights. We're also going to be talking a little later on about the building trade-off option, a computer simulation method. Some of the mandatory requirements are for submittals and product information, data sheets and certification sheets from manufacturers that must be submitted. The envelope components enclose a conditioned space or a semi-heated space. Semi-heated, a heating system with a capacity larger than 3.4 BTUs per hour, but not cooled. It's called a semi-heated space. And the code has tables that have 3 categories within them. And the categories are non-residential, residential, and semi-heated. So we're going to be looking at the non-residential and the semi-heated. In other words, heated but not cooled. And within the code, the spaces must be defined according to whether they are occupied or whether they're unoccupied, whether they're insulated, partially insulated, or uninsulated, and what they're next to. Is a conditioned space next to the outdoors? Is it next to an unconditioned space? Or is it next to a semi-heated space? So all of these space definitions appear, that the requirements differ between them. And primarily we're looking at conditioned space and semi-heated. The conditioned would be in the non-residential category. Now, spaces in climate zones 3 through 8, which is ours, are assumed to be conditioned unless the space will be only semi-heated and unconditioned and approved by such for the building official. So you as a builder or a designer have to designate these spaces, and you say, look, as you go to the building official, here's what we're planning on doing. This is an unconditioned space. We're not going to heat it. We're going to heat it minimally, and that's the reason we've chosen these parameters, this insulation level of the building envelope. Now, alterations, remodeling. They have to comply with the requirements of Section 5, but there are some exceptions. A number of exceptions. Storm windows. I continually see old buildings, particularly historic buildings, maybe rehabs in blighted downtown areas where they're using the old metal windows, reglazing them, and simply putting storm windows over them. That does not need to comply with the new Energy Code. Replacement of glazing in existing sash and frame. That's a baseball through a window. If you got a broken window, you can replace it with the same type of glass that's there originally. Alterations to envelope cavities, provided they are insulated to full depth with a nominal R3 per inch insulation. In remodeling, you open up a wall or you open up a cavity that's supposed to be insulated and you find it's fully insulated, you're home free. You don't have to bring it up to new code requirements. With a nominal R 3.0 per inch. That is the R value for fiberglass insulation, 3.0 per inch. Roof and floor alterations where no new cavities are created. That's pretty simple. Replacement of roof membranes, re-roofing. A commercial building, you don't have to comply. Commercial roofs are typically flat roofs. They used to be 3-ply asphalt built-up roofs, felt in asphalt or felt in coal tar pitch. They're now becoming more single membrane roofs with plastic or rubber of one kind or another. Replacement of existing doors, and this is quite frequent in places like hotels where the moving crews, the setup crews are moving large pallets full of tables and chairs in and out of the doors, and the doors get scarred up all the time. And so, in spite of their best efforts, they have to replace these doors periodically. So, if there are exterior doors, you don't have to comply with the new code in replacing damaged doors. And you can replace up to 1/4 of the windows in a building without having to have the new windows comply with the new energy code. Now, we used to have climate bins. That has been changed now to climate zones. And the climate zones are listed here and in Appendix B on a county-by-county basis for the United States. And here's an enlarged view of that. This new climate zone system is common to all the new federal documents, to our residential building code, to the commercial building code, and any other of the federal documents that refer to climates. There are 8 climate zones. Climate zones 5, 6, and 7 fall within the state of Michigan. You normally think of climate zones as changing as you go from north to south, but look at this little anomaly right here in the Upper Peninsula, where climate zone 6 actually intrudes in the middle of climate zone 7 in the UP. And the climate zones have A, B, and C designations. A in the east is a moist climate zone. Tropical moisture from the Gulf comes up through this area in the summertime. The mountain states are climate zone B, and we have a marine climate C, which extends all the way down into almost Southern California. But notice there are portions of a climate zone that can be in A or B. Here's a 5A, here's 5B, 6A and 6B. In marine, we've got 4A, 4B, and 4C. So anyway, climate zones 5A, 6A, and 7 appear in Michigan. And you'll be happy to know the people in the Upper Peninsula share a climate zone with Alaska. Here are the tabulated data. 5A, heating degree days between 5,400 and 7,200. 6A is between 7,200 and 9,000. 7 is between 9,000 and 12,600 heating degree days. And here is a map of the state of Michigan, taken from the Michigan Energy website. And there's our little anomaly in the Upper Peninsula, but look at this. Right in this part of the state, instead of going from north to south to change climate zones, you go from east to west, right here, these 2 counties. That's a little anomaly that you should be aware of. And here they are enumerated. You can actually see printed in legible form which county is in which climate zone. Now, in complying with the envelope requirements, there are several paths to follow. You have to do certain things, mandatory provisions. Then you can do either the prescriptive or the trade-off. Or you can use a third one called the energy cost budget method. Those 3 methods. Some of the mandatory provisions in insulation, all of these requirements, you have to label it. Substantial contact, recessed, we're going to cover all of those right there. And air leakage. Used to be that we would stuff scrap fiberglass insulation around the outside of a window during construction. Now we'll be looking at foaming that with an expanding foam, such as a polyurethane foam, to seal up the windows. We have to seal them in accordance with NFRC 400, National Fenestration Rating Council Standard number 400. And loading docks in climate zones 4 through 8 are also covered, and vestibules are covered. They want us to seal up the building, and sealing to reduce infiltration becomes a major part of this new energy code. They're looking at all sorts of places, and the code even suggests places for you to look and to seal and to caulk and to put air barriers. And the code outlines all these places, suggests where they should be seen. Fenestration Rating Council, air leakage right there in that little box is a requirement. Swinging entrance doors and revolving doors have a limit of 1 CFM per square foot of infiltration. All other products not to exceed 4/10 of a CFM per square foot. And you'll see that this window has a leakage rate of 2/10, so it complies. However, garage doors are exempted, and any windows and doors that are fabricated on the job site, field fabricated, obviously cannot be shipped back to the factory to be tested. At the loading dock, they ask us to put a weather seal, a big cushion in which the delivery truck backs up against it. The back of the truck seals against this and prevents air infiltration when the door is open. We're now required to put in vestibules. Now, vestibules have to allow one set of doors to close before the other set can open. And if a person in a wheelchair is in there, he has to be able to manipulate these doors. So there has to be at least 7 feet between the doors of a vestibule. The doors have to be self-closing, and they cannot be open at the same time. Now, there are some exceptions. Doors that are service doors. They're not for public entrance. Mechanical room, loading docks, things like that do not have to have vestibules. Revolving doors. Small buildings, less than 1,000 square feet in our climate zones. Or, here's another one. Buildings that have doors that open from spaces less than 3,000 square feet that are separate from the building entrance or from dwelling units. Now, that's an unusual one. You have to think about it. A good example would be an indoor shopping mall where there are main entrances to the interior corridors in the mall. But yet some buildings have their own exterior entrances. Restaurants, for instance, might have their own exterior entrance. Well, that door, if the space is less than 3,000 square feet, does not have to have a vestibule. To comply, to use the building prescriptive option in complying with the code, in other words, do it like it's printed in your home free, you can have no more than 40% of the exterior gross wall area as in windows. No more than 5% of the roof area in skylights. Any more than that, and you have to use another method of demonstrating compliance. Now, for each climate zone, there is a set of tables. And there are 8 climate zones, so there are 8 tables. And within each of these tables are summarized all of the thermal transfer values, the R values and U values for all of the building exterior envelope components. They are categorized into the 3 categories again: non-residential, residential, and semi-heated. Obviously, we will not consider the residential portion of those tables. They cover the envelope, which is roofs, walls, floors, and doors, and fenestration. And here's a summary for Climate Zone 5, non-residential. The table for 1999 version, the previous code, all those values are in red. So here's what's happened from 1999 to 2007 in our commercial energy code. For roofs where the insulation was entirely above the roof deck, in other words, a flat built-up roof, used to have a requirement for R15 continuous insulation. That is now R20. For a roof with an attic and blown-in insulation, it used to have an R30 requirement. Now it's R38. For above-grade mass walls, and a mass wall would be a concrete block, brick, heavy wall with a thermal flywheel effect where it tends to retain heat. They used to have a requirement of 7.6 R of continuous insulation in the wall. Now it's 11.4. Steel framed walls above grade used to have an R13 insulation plus R3.8. Now it's an R13 insulation in the cavity plus an R7.5 continuous sheathing. Wood framed walls used to be R13. Now they're R13 plus R3.8 continuous insulation sheathing. Below grade walls, basement walls, didn't have to be insulated at all in the previous code. And now they're asking for R7.5, which would be 1.5 inches of extruded styrene insulation. Concrete floors, mass floors, R8.3. Now this is a floor over an unheated basement space or a crawl space. A utility space that didn't have any heat in it used to have R8.3 under the slab. Now it's 10.4. Steel joist floors over unheated spaces used to be R19, now they're R30. Slab on grade floors, heated, which means hot water radiant heat in the slab or underfloor ductwork around the perimeter of the slab, used to have R10 for a depth of 36 inches. Now it's R15 for a depth of 24 inches. And non-swinging doors had a U value requirement of 1.45 before, now it's 0.5. So the designers in the documents now that go to the building official for plan review for the permit application have to specify all these things. It's not sufficient just to give a building outline. In the documentation, you must provide the details of the R values, the U values, and all of the different thermal requirements of the structure. Now, I will say that it's been common practice in the past to have a set of drawings, plans of the building depicting the different floors and elevations, and then a printed document, a book which is a set of specifications. And many times, only the plans were submitted to the building officials for a permit application. And all the information on the products that were contained in the specification book never got submitted. So the architect has two choices, and he has to talk with the builder who's actually going to supply the plans and specs to the code officials for the review. The builder has to know that that data has to go to the plan reviewer. So he either submits the book of specifications or he has the architect put all that stuff on the drawings. The tables that we talked about mentioned the R value of insulation. That is only the insulation component of the building envelope. Does not include the studs, the framing, the sheathing, the siding, anything at all, the air surfaces. It's only the insulation component that we're talking about. However, we can use the overall U value heat transfer. In order to do that, we go to the Appendix A. And in Appendix A, there are myriad different variations of wall construction and ceiling and roof construction. And they have calculated the U values. They've put different insulation in, different sidings, different sheathings, and they have calculated the U values. If you're going to use the U value, the U times area alternative, rather than just listing the insulation itself, then you're going to go to Appendix A and pull those values. Again, the roof insulation must meet the values that are shown in those tables. Skylights in the roof. They can be no more than a certain area. Remember, for the prescriptive method, no more than 5% of the roof. And skylight curbs have to be insulated. And the insulation is specified there, at least R5. 3 types of roofs. Roofs with insulation entirely above the deck, metal building roofs, and attics and other roofs. Metal buildings are treated in a different way. It used to be that the metal building roofing material, which is a corrugated steel or painted metal of some kind, was actually screwed tightly to the purlins. And where the insulation was draped over the purlins in the past, it got squished to nothing. And the insulation used to be a 2-inch or 3-inch thick fiberglass roll, 6 feet wide, faced with a vinyl vapor barrier. And they would simply unroll it on top of the purlins and then put the roof panels on and screw them tight. Well, now they're treating them a little different. Metal buildings, they're talking about draping the insulation one direction over the purlins, then another layer of insulation crossways parallel to the purlins, and then having spacers at least 1 inch thick that space the metal roofing off the insulation so it doesn't get squashed to nothing where the roofing is screwed down to the purlins. Now they have what they call a high albedo roof, and that's basically a light colored reflective roof, reflects the sunlight. It's a cool roof. and they allow you to put less insulation in the attic or under a cool roof. Now, above grade wall insulation, as we talked about, 4 types of walls are defined. Mass walls, again, walls that have a high thermal flywheel effect, that tend to gain heat and lose heat slowly, like the combination block brick buildings common in many college campuses. And they talk about having continuous insulation, basically between the block and the brick or other types of heavy mass construction. And the requirements shown in the table are for continuous insulation. There is an exception, however. If you can demonstrate the overall U value of that wall is less than 0.15, then you don't have to worry about all the details of installing the insulation. Now, there's a metal building wall R value, a steel framed wall R value, and a wood framed and other type of wall R value. Each has its own details of how you're to install the insulation. Below grade wall insulation, we didn't used to have any for commercial buildings. Now we're required to have at least 1.5 inches of insulation. It's continuous insulation. In floors, and these would be floors over unheated spaces, crawl spaces or unheated basement spaces. It says that you have to insulate the floor, and you have to put the insulation up in contact with the floor above, with the subfloor. And again, they talk about mass floors, which are concrete floors, steel joist, and wood frame floors. Slab on grade floor insulation. This is very common in commercial buildings. Many small strip malls and individual office buildings are designed with slab on grade. And there are specific requirements for installing the insulation on slab on grade buildings. You can put it on the exterior. You have to protect it from damage and sunlight on the exterior. You can put it on the interior. However, this is an interesting little application that is permitted in residential construction, but not in commercial. They say they want it vertically in commercial, either on the inside or the outside. Now, if it's on the inside, keep in mind that we're talking about the full thickness of the perimeter insulation now. It used to be that we would have simply a thermal break, which might be a 1/2 inch wide gap filled with some kind of an asphalt mastic material. Well, now they want the full thickness of the perimeter insulation, which is at least 1.5 inches now. So if you're going to be putting this in, and you have a stretched carpet, which requires tack strips, how do you fasten the tack strip down? Where's it going to go? Well, it's going to go within 1.5 inches of the wall. And at an earlier presentation, a code official raised his hand, and he said, what I'm allowing them to do is to construct the top 8 inches of the foundation wall out of a 4-inch concrete block. And then the wall above it, whether it's a 2x4 or a 2x6, overhangs that insulation and actually covers it up. So you don't have to worry about how to fasten a tack strip down. Well, there are a number of ways to do that, and that's just one of them. The tack strip can be glued down at the very, very edge of the concrete, and then a mop board applied on the inside wall might provide enough overlap to tuck the carpet under. So there's several different ways, but it's up to the designer to think about how you're going to apply stretched carpet on an application on a slab-on-grade floor. Opaque doors. In the 1999 code, swinging non-residential doors, which is the commercial doors, entrance doors that we have, used to have a U value of 0.7. It is unchanged. However, non-swinging, non-active doors, the U value was quite lenient, 1.45. Now they're saying it also has to have a U value of 0.5, which is less heat loss than a swinging door. Semi-heated is unchanged. Fenestration, a fancy name for windows and doors and skylights. There's a solar heat gain coefficient that also applies. And we must have these ratings tested in accordance with the National Fenestrating Rating Council, which says that an independent testing laboratory has to certify the values of the heat transfer, which is the U value, the air leakage that we talked about already, or the solar heat gain coefficient. Now, the residential code does not require compliance with solar heat gain coefficients. The commercial code does, however. So that you folks who are building both residential and commercial structures know there's a difference. You can get away without having to worry about solar heat gain for residential, but you must worry about it for commercial. And again, using the prescriptive option and complying with the code, we can use no more than 40% of the outside wall area as windows and no more than 5% of the roof area as skylights. And the maximum fenestration U value for metal frame windows in climate zone 5A is 0.45 and the solar heat gain coefficient is 0.4. And again, zone 7, the Upper Peninsula, 0.4 and 0.45. In many commercial applications, you will find a coated glass, a colored glass, a reflective glass. And these are metallic coatings that are applied to reflect sunlight and reduce heat gain. They can affect visible light transmittance, and they can also obviously affect the size of the air conditioning system. So solar heat gain goes right along with the heating and air conditioning system. Now, the visible light transmittance is not considered when we're using the prescriptive option. However, if we're using any of the other compliance methods, the trade-off methods, ComCheck, we must consider the visible light transmittance. So in the climate zone tables 1 through 8, we'll find the requirements for the fenestration, the U values and the solar heat gain coefficients for all the different climate zones. Now, building overhangs can be used to modify these solar heat gain requirements for the glass. So if the architect designs a structural overhang that shades the window, then you don't have to have as strict a solar heat gain coefficient. And if you find yourself in an application where you cannot get a glass with the required solar heat gain coefficient, then you can do an exterior shading. And this is very effective. However, you'll find that the shades don't need to be very deep to be very effective. 3 inches is a good starting point, and you can get that quite frequently by simply recessing the window to the inside of the wall, having it flush with the inside rather than the outside of the wall. Now, the building envelope trade-off option, envelope performance factor, requires a computer program. We're getting away from the prescriptive option. This is one of the options, not prescriptive, that requires a computer program to compare 2 buildings. And the 2 buildings are actually the one building that you have designed or the architect has designed. And in one instance, you apply all of the architect's requirements, specifications for windows, for thermal performance of the walls and windows, the U factors, the R values, and you run a computer simulation to see how much energy the building's going to use, size the heating and air conditioning equipment. Then you make a copy of that building and you go back and modify all of the U values and the R values to the minimums specified in the code. And then you run another computer simulation of that building. The 2 buildings are identical except for those U values and R values. And you compare the 2. And if you exceed the code by a certain amount, then you comply. You at least do better than the code. If you do better, you have complied with what's called the envelope performance factor. Now here's again requirements in more detail. Labeling of the building envelope insulation, and labeling is easily done if the insulation has a facing on it, whether an aluminum foil facing or a craft paper, because it's easy to print the data on the insulation facing right there, the R value, and any other data. However, if you have a loose fill insulation, a bad insulation, blown in insulation, sprayed on urethane or isocyene or any of the other insulations, sprayed on chopped cellulose insulation, then you have to rely on manufacturer's data, certification from the manufacturer and the applicator that the insulation installed in this manner, in this thickness, will guarantee this R value. And so those things must be submitted as part of the package. That's requirements. We have to have baffles to prevent the insulation from closing up natural ventilation of the attic. We talked about substantial contact, recessed equipment. All of these things we're going to talk about here. The installation of insulation has to be limited to slopes that are less than 3 and 12. Now imagine a scissors truss where the inside slope would be not the exterior roof slope, but somewhat less. And if it's more than 312, you cannot apply a loose fill insulation simply because of the fact it's going to slide downhill. So the insulation has to be installed in such a manner as to achieve its rated R value. If you have E-vents, in other words soffit vents here letting attic ventilation up to a ridge vent, you have to have little baffles to prevent the insulation from closing off the ventilation path. And there are some exceptions, talking about a metal building. Insulation in the floor has to be in substantial contact with the underside of the floor surface, and it has to be supported in a permanent manner. Can't rely on friction to keep it from falling out. Equipment in a ceiling that's insulated is limited. You can put recessed light fixtures in a ceiling. They have to be IC or insulated ceiling rated, but they can be no more than 1% of the area. However, I like to design a building where we don't compromise the insulation at all. We have the full insulation over all of the recessed equipment that punches holes in our insulated ceiling. This is my feeling as a professional engineer, although the code does allow up to 1% of the ceiling area to be exempt. We have to protect the insulation. Here's an example of an attic scuttle opening where you'd have an attic access panel. You have to get a step ladder, lift this out, and then poke your head up into an attic. And this panel, the lift-out panel, has to be insulated now to the same R value as the rest of the attic insulation. Keep in mind that this is a movable panel, that you're going to be taking it in or out. The maintenance people will be over the life of the building, and so that insulation has to be something that will withstand moving and withstand any kind of rough handling. So instead of a loose fill insulation or a fiberglass bat insulation, we'd be looking at a foam insulation of some kind. And keep in mind that many foams are not fireproof. They have to be protected from human contact by some kind of a fire barrier, either a cement board or a gypsum board. So that would be a good location for a gypsum board right on top of the plywood here. Also, the weather stripping and the infiltration requirements are such that we now want to prevent infiltration around this attic door, and so we're looking at installing weather stripping at this point. Roof insulation. If you have a suspended ceiling under the top floor of a building where you have roof insulation, you must not lay that insulation on the top of the lay-in ceiling. Taking the ceiling in and out to service things over time would displace that insulation and make it totally ineffective. The insulation must be fastened either as part of the roof deck or fastened underneath the roof deck. Fenestration and door U values have to be as those appear in the table. Again, 100 is for the thermal performance. Solar heat gain is standard 200. And visible light transmittance is covered in another standard. Standard 400 is the infiltration. Skylights can be in a sloping roof. The skylight U value has to be rated by the manufacturer for a sloping roof or a horizontal roof. And they say rate it for a roof of 20 degrees above the horizontal. And the reason is the U value of a skylight will change depending on the slope of the roof because of thermal convection currents on the inside and on the outside of the skylight. Air within about 1/8 of an inch of a surface tends to cling to the surface, and it forms an insulation barrier. If that air is moving, the barrier is thinner. And so the steeper the roof, the more convection currents, the less insulating value the air surfaces will have. And so you must rate a skylight at a sloping roof, and the code says 20 degrees. Again, 5% maximum. We do have some exemptions. Solar heat gain coefficient is part of the rating system for fenestration. And here is some exceptions. Solar heat gain coefficient is an update of a term called shading coefficient. And here's the relationship between shading coefficient and solar heat gain coefficient, 0.86. And a little description of the effect of solar heat gain in reducing building heating and cooling loads. Visible light transmittance, again, if you're not using the prescriptive option, if you're using one of the other trade-off options for demonstrating compliance, the visible light transmittance is part of the code requirement. Now we're done with the building envelope, and we're going to talk about the heating and air conditioning portion. And this is the major portion of the Commercial Building Energy Code. It's about half. Now we can use the same options, prescriptive, trade-off, energy cost budget, but there's something also that can be used for HVAC, demonstrating compliance with the code, and that's called the simplified option. We'll be covering that. So when we're altering a building, not constructing a new building, but doing remodeling or alterations, the new equipment has to meet the requirements of the new code. Heating equipment, air conditioning equipment. The ductwork shall comply. New and replacement ductwork shall comply. Sealing and insulation. Piping, the new and replacement piping must comply. Alterations have some exceptions. If you're repairing something, if you're putting a new fan motor in, if you're replacing the temperature controls or the burner controls or whatever, you do not need to bring the device up to the new energy standards if you're not going to reduce the efficiency. If you cannot get a new piece of equipment in without moving everything around in the mechanical room, revising ductwork, relocating controls, all sorts of other devices, if you cannot replace the equipment with new, highly efficient equipment, then you are allowed to replace it in like kind. You're not required to comply with the new energy code if you're simply replacing refrigerant. Or you're relocating a furnace. Maybe you're moving something out of the way to provide a better access. Existing equipment simply moved a little bit, you don't have to worry about it. And ductwork and piping where there's not sufficient space or access to meet the new code. You simply cannot get the required level of insulation around the pipe because there's no space in the chase. You don't have to comply. But again, these things have to be reviewed with the building code official, the authority having jurisdiction, to show them what the problems are. And it's a good idea to approach these things beforehand, before the project starts construction. So you're on the same page, you're talking congenially, and you're working towards a common goal. Now again, there's different methods of demonstrating compliance for HVAC equipment. We do have some mandatory requirements, and they are minimum equipment efficiency, and there's all sorts of tables in the code for all sorts of different pieces of equipment. Heating and air conditioning equipment 5 tons and under is classified as residential. The efficiencies are covered by legislation passed by Congress, and we know the minimum heating efficiency is 80% for furnaces. For air conditioning, it's a SEER of 13. And for water heaters, it's called a heating factor of 0.62. That's the efficiency. It's actually a firing efficiency of more than 62%, but then we lose heat through the jacket of the water heater, which lowers it down. So that's the minimum efficiencies. But for commercial equipment, we're talking bigger things. 6, 7, 8, 10, 100 tons, 1,000 tons. Things larger than residential are covered in all sorts of tables in this book, the efficiencies of all these different pieces of equipment. That's mandatory, have to follow that. Then if we have a small building, we can use a simplified approach, which is allowed only for HVAC. Or then we can go to the prescriptive path or the energy cost budget method. The simplified approach is available for the majority, I would say, of new commercial buildings. The majority of new commercial buildings are like strip malls, doctors' offices, small retail spaces. And it's limited to 2 stories or less and 25,000 square feet or less. If your building falls in this category, you need to comply with only the requirements of 15 paragraphs in the code, and you're done. You're home free. That's called the simplified approach. First of all, we're looking at a single zone heating and air conditioning system. Now, it doesn't say how many zones you can have in these buildings. There's no requirement, no limitation, but that each zone have its own heating and air conditioning unit. The systems have to be air-cooled or evaporatively cooled, have to have an economizer unless you increase the efficiency of the air conditioning system so that you can get away without an economizer. Economizers are limited to unitary systems, and it can be an EER trade-off according to system size or climate zone. Now there's some little requirements in there, but they're very easy. Some of the other options are we have to have a dual set point thermostat or a manual changeover from heating to cooling to make sure that we do not do simultaneous heating and cooling. Don't have the furnace running at the same time as the air conditioner. Supplementary controls for heat pumps are covered. We cannot do simultaneous heating and cooling for humidity control. Time clocks are required. Basically, it goes on to describe in a big long paragraph the description of a programmable thermostat. So that is a requirement. The piping and the ductwork has to be insulated. The systems have to be balanced. They have to be adjusted after they're finished. The thermostats have to be interlocked. Again, if you have thermostats in different zones, the zones might touch one another. You cannot have one zone heating at the same time as the other one's cooling if they're adjacent to each other. And if you have exhaust systems greater than 300 CFM, they have to have dampers on them, gravity dampers or motorized dampers that seal tightly, unless the systems operate all the time. And if the system is large enough to be 10,000 CFM or larger, it has to have what's called an optimum start control. And that's basically a thermostat system that learns over a period of time the thermal flywheel performance of the building and starts the furnace or the air conditioning system appropriately in advance so that it's up to temperature or down to temperature by the time the occupants come at 8 o'clock in the morning. So again, the mandatory provisions are in addition to the efficiency standards, we have to provide load calculations, and these are computer programs simulating the building. We have to size the heating and cooling systems, and we use a computer program to do that, and the results of that have to be submitted to the building official as part of the building permit application process. There are temperature controls that we're concerning ourselves with, the insulation, the construction of the system, sealing the ductwork and insulating it. Equipment covered under the code now that is not. We're outside the simplified approach and we're talking about the full-blown compliance approach for large systems and equipment. These are what are covered: package, air conditioning and condensing units, heat pump, PTACs, package terminal and room air conditioners, chillers, including absorbers. They may be very large chillers, furnaces, unit heaters, boilers, and heat rejection equipment like air-cooled condensers. The efficiency is covered in all sorts of tables. Not going to go into those. Furnaces with input ratings greater than 225,000 BTUs per hour cannot have any kind of a standing pilot light for the ignition source. Got to be something spark or some kind of a glow coil ignition. They have to have some kind of a jacket insulation in the sheet metal housing of the unit. The equipment efficiencies, the Energy Policy Act, EPACT, appliance to comply with the DOE certification requirements. That is one program. Trade organizations like the Air Conditioning and Refrigeration Institute, ARI, have rating systems for equipment manufactured by their members so that you can compare one against the other. It's a uniform system of rating. You must supply these efficiency ratings as part of the building permit application package. The product data has to be verified by an independent agency. Where an independent agency has no standard for such data, for such products, then you have to have the manufacturer's test data. Have to rely on the manufacturer and hope he's telling you the truth. And different manufacturers are sometimes put together in a system. Well, the overall system efficiency has to be somehow demonstrated by the engineer who designs all this combination of things. So equipment efficiency has to be demonstrated on a permanent label on the device, the furnace, the air conditioner, whatever. Now there's an interesting exception to the new energy efficiency requirements, and it's for little bitty PTACs. Tiny air conditioning and heating units don't have enough space in them to have large enough evaporator coils and condenser coils to get the efficiency that the code now requires. But the people writing the codes understand that there's millions, literally millions of them in the United States in existence, in buildings, and they fail. They have an actuarial life of somewhat less than 15 years. Now, the new energy code says that replacement equipment has to meet the new energy standards, but they realize that they cannot. So they have allowed the manufacture and purchase of these small PTACs that do not meet the efficiency requirements, but for use only in retrofits in existing building, replacing dead equipment. They cannot be used in new construction. So as designers, do not incorporate these little substandard energy efficient PTACs in your new designs. Now again, the engineer must demonstrate the sizing of his equipment. He has to submit the printout sheets from his heating and cooling load calculation programs. For the thermostats in the units and the control zones have to have deadband controls. And what that means is that for a 5-degree range around the standard temperatures for human comfort, between 70 and 75 degrees, the system does nothing. It does neither heating nor cooling. Everything is off. That's called a deadband. Now there are some exceptions to that. Special occupancies, maybe retirement homes, but you have to clear this with the local code officials before you apply any systems like that. You cannot have any overlap between heating and cooling. Many commercial buildings use central computers. They're called energy management systems or sometimes direct digital control systems. So a remote computer, maybe in another building, like on a college campus, would be controlling the temperature in your space. There'd be a temperature sensor there, but the control is actually remote. Well, the code talks about how that computer is supposed to control the temperature in your room. Off-hour controls. Basically, when the system is not needed, shut it off. At night, we don't want air conditioning. Certainly in warm climates, the temperature will rise. In cold climates, such as where we are in the wintertime, we can let the temperature drop. We can let it cool off. There are certain minimum limits, however. If we let it cool off too far, it'll take all day the next day to warm it up again. So we do have some off-hour controls. They want the system to shut down automatically or to set the temperature back. The optimum start, as we talked about, is a learning algorithm in the thermostat that actually over time sees how the building responds, how long it takes to heat up and cool down. And we have to isolate zones from one another with different zone controls. And again, there are some exceptions, notably heating and air conditioning systems less than 15,000 BTUs, about 1.25 tons. Have to shut the systems down with an automatic 7-day time clock. It has to have a battery carryover in case of power failures. Or you could have an occupant sensor. Many of the offices in buildings now, instead of light switches, have occupant sensors. When the occupant leaves the room, the lights go off. And they want us to set the temperature back at night down to 55 degrees or less. Optimum start controls, as I mentioned before, the system learns the performance of the building. It takes into account how long it takes the building to heat up or cool down. Isolate the zones one from another, have temperature controls and systems for each of them. The optimum design is to have individual temperature controls for each person in a building. Each person at his workstation or office would ideally have an individual temperature control. It may not be possible economically to do that. It may cost too much. So at the very least then, they say if you have to group these individual spaces together in a zone, have them all have similar heating and air conditioning requirements and have one thermostat control that group of spaces with the similar heating and air conditioning requirements. And when they differ, such as on the exposures of a building, the north exposure and the east exposure and the south exposure would all have different zones. They would have different controls as well. On dampers for stair and shaft vents, They want dampers, motorized dampers, if the building is 3 stories or more high. Shorter buildings, 1 and 2 story buildings, stairwell vents, for instance, venting smoke from an exit stairwell at the top in the roof, they can have gravity dampers rather than powered dampers. The motorized dampers automatically close during normal building operation. These would be for the elevator shaft or the stairwell vents, and they would be opened as required by the fire and smoke detection systems. And sometimes there are even requirements for pressurizing the stairwell with outside air, with clean, fresh air, to keep the smoke away from the means of egress. Gravity dampers are okay in the lower climate zones 1 through 3, and in short buildings. Ventilation dampers, dampers bringing outside air into the building for breathing purposes, have to be shut down when the building is not occupied, or when the building is coming up to temperature in the winter or down to temperature in the summer. They want full recirculation in the building. An exception is when you're actually using the outside air to help cool the building in the pre-dawn hours. Again, the shut-off dampers and the damper leakage rates are specified. They have to seal tightly with maximum leakage rates as specified in the code. Now, where outside air and supply and exhaust air dampers in the building ventilation systems are required, again, they have these leakage rates, and they're certified in accordance with the Air Moving and Conditioning Association Standard 500. Ventilation fans larger than 3/4 horsepower shall have automatic controls capable of shutting off the fans when they're not necessary. So not only the heating and air conditioning systems, but any other fans operating along with it. And the only exception is if they're intended to operate continuously for some unusual reason. Heat pumps have to be sized exactly. They don't want to oversize the heat pumps, and they are allowed to have some supplemental heating. And it can be electric resistance heating. If the heat pump is not capable of heating the building to the required temperatures in the middle of the heating season, in the wintertime, we are allowed to have some supplemental electric heat. But they have to have controls. Automatic valves are required for humidifiers. If the humidifier has a preheat system, or if it boils, if it has a boiling chamber full of hot water and it evaporates and makes steam, when the system is not required, they don't want the boiling chamber hot. They don't want it to stay hot all the time if humidification is not required. You have to prevent the simultaneous operation of humidifiers and dehumidifiers, just like we did with heating and cooling. Make sure they don't operate at the same time. There are some exceptions. Freeze protection, snow melt systems. They say basically when it's not needed, shut it off. If it's warm outside, shut it off. If it's below freezing outside, it's a snow melt system and it's not snowing, shut it off. If you have heat tape protecting something and it's below freezing, obviously you want it to continue running. But above freezing, shut it off. Ventilation controls for high occupancy areas, lots of people. There is a new concept called demand-controlled ventilation. And that's basically a system that senses the carbon dioxide in a room. That's the only current method they have. They feel it's reasonably reliable of determining how many people are in a room. It's difficult to count people automatically with some kind of a control system. So they measure the carbon dioxide, which is the measure of how much we're breathing out. And they can infer then that there's lots of people in the room, the carbon dioxide is increasing, we better get some more fresh air in there. So anyway, they want demand-controlled ventilation for areas larger than 500 square feet, more than 40 people per 1,000 square feet, where there's an economizer on the air side, an outside air damper that's modulating, and an airflow greater than 3,000 CFM. There are some exceptions, however. When you're building the ductwork and the piping, they say you have to insulate it, and you have to seal it, and you have to test for leakage. The insulation has to be installed in accordance with the instructions. Protect the insulation. It has to be protected from sunlight. If it's outside insulation, from sunlight, from mechanical damage, from hail damage, from water damage. If it's down near the ground, from lawnmowers and string trimmers. If you have ductwork outside, and this used to be the case that there was not space inside a ceiling for ductwork, an air conditioning apparatus and ductwork might be outside on the roof. I've seen a number of buildings that way. It was very difficult to find an insulation protection system that could withstand ultraviolet light for years at a time in temperature extremes. So many systems now are being designed with internal insulation in the ductwork, and the ductwork is soldered watertight. And the zinc-coated galvanized ductwork withstands ultraviolet light quite well and withstands rain and the weather and the heat in the summer and the cold in the winter. So the galvanized ductwork, soldered watertight, is a very good weather protection with internal insulation. However, water piping on the outside of the building cannot be insulated internally. So if you have piping outside, going to a rooftop chiller, for instance, you have to protect this piping insulation, and typically they're now doing it with an aluminum jacket, sealed tight over the outside of the insulation. Return and supply ducts and plenums have to be insulated, and there are a number of exceptions. And the ducts located within the heated, semi-heated, or cooled spaces. Now the operative word there is spaces. So if you had ductwork above a ceiling in the corridor, you'd have to insulate it. But if for some reason that ductwork was exposed within the living space where the people were, it would look very bad, obviously, but it might have to be for one reason or another. You need not insulate it. And you find this in many bars and restaurants now, where the ductwork is exposed. Spiral ductwork, very sturdy. It's painted. It's exposed. Sometimes it's painted in bright colors to be part of the decoration. Sometimes it's painted in flat black to disappear into the ceiling spaces. But they have no ceilings. They are open roof trusses. Piping is exposed, wiring, conduit, and ductwork. So in that case, you do not need to insulate the duct. Short runouts of duct to air terminals do not need to be insulated. And again, another exception for the back sides of air outlets and plenums exposed to unconditioned spaces if it's just a little bit, less than 5 square feet. Piping insulation. Piping carrying fluids below 60 degrees Fahrenheit and above 105 degrees Fahrenheit have to be insulated. The exception to that is any water that might be solar heated, any kind of naturally heated or cooled water, maybe lake or river water where you're not using fuel to heat or cool it. You need not worry about the insulation. It says hot water piping between the shutoff valve and the coil, not greater than 4 feet in length when located in conditioned spaces. Basically, if you have difficulties insulating things because of valves and controls, unions, relief valves, whatever that might be close to heating or cooling coils, you need not insulate that little bit of piping. And they say pipe unions in heating systems. Pipe unions are used by the service person. If he has to remove the boiler, the coil, the pump, whatever, he has to find a place where he can separate the piping. And if you insulate over the pipe union, he can't find it. He doesn't know where the union is, or even if there is a pipe union. So they're saying, please don't insulate over them. So let's